So all I want you two to do is just hold those two things there. Start of the video, first 10 seconds max. Okay, I'll take them off of you and then you can go back to whatever it was you were doing. Okay, is that fine? Cool? Questions? Good. Okay. Hey there everybody, my name's Bill and welcome to Crazy Grandad. This may come as a shock to some of you, but I actually do a bit of 3D printing. Yeah, I know, hard to believe. As is the case with a lot of people that 3D print stuff and whatever, we find a lot of problems with 3D prints breaking. All right, they're not as strong as a injection molded plastic part a lot of the time, and people experiment with ways to try to mitigate that or try and make 3D prints stronger. One of those is annealing. So today I'm going to have a go at annealing some 3D prints. You know, we all use 3D printers to make up little bits and pieces, you know, for whatever we're doing, you know, little oddments or parts, ornaments, whatever. Ornaments, not so much a problem, but if you're making something that's got to do a job, it's got a purpose in life, then you don't want it to break. You don't want it to fail while you're using it. So a lot of the time, you know, there's ways around this. You can sort of think, well, you know, as long as my layer lines are going the right way and this, that, and in the case of something like this is okay. But then there are other times where you just kind of can't get around it. So you know, you're forced to sort of either cross your fingers and hope for the best or look for another way. So today we're going to investigate that other way. So what I've done is I have printed some parts. I've just gone into Onshape and just threw these together real quick. They're nothing in particular. They're not like a test print that you can download or anything like that. Well, you can because it's a public file now, but this is just something I kind of threw together, and what I've tried to do with this is incorporate a few things into a simple geometric shape that would bring about what I suppose would be weak points in a normal 3D print. So you may notice I have a C, I have an A, and I have an AF, otherwise known as calf. This is basically a control. So with that one, we're not going to do anything. We're just going to leave it as is. This one, I'm going to anneal in the way that I have seen. You hop on like, you know, different forums, Reddit, wherever, and it seems to be the general way of annealing 3D prints, especially with PLA. And that is to basically heat up an oven to, you know, whatever your print temperature is, sort of, you know, 190, 200, 210, whatever. And then you have your part ready to go, and then basically you put your part in the oven, and as soon as it goes in, you turn the heat off and let the oven just cool down, just let it chill out. And then you bring the part back out when everything's cooled down. And apparently that's the way to do it. So we're going to try that with that one. This way is a way that probably not many have heard of, but I've seen it sort of mentioned a couple of times here and there. And the AF stands for annealed with flour. That's right, flour, baking flour, FLOUR, flour. So apparently the story is you take your part, you put it in a, I don't know, should we say a baking tin, for lack of a better word, baking pan, and you bury it in flour, and you completely pack it in flour and try and compact it in as much as you can, right? Think what a foundry worker would be doing if they were making a part out of cast iron, right? It's like the sand for whatever. So And then the idea is similar to normal annealing, but with a couple of differences. You heat up your oven to your desired temperature, you put it in there and you leave it to bake, I suppose, at that temperature for about 30 minutes, right? About half an hour at temperature. Then when you get to that 30 minutes, then you turn the heat off and let it cool down. So it's a bit of a different story to, we'll call it the conventional annealing. So we'll give that a try with that one and see what happens. So these have all, obviously they're all identical parts. They've all been printed with the same parameters. I won't go into the details right now, but you know, they're sort of, you know, I think what, 4-layer wall thickness, about 40 or 45% infill, cubic infill, standard sort of thing, or what you would ask for if you wanted a reasonably structurally sound 3D print. So we'll try that with them. Now another one that I've got another one of these same shapes printing at the moment, but it's something I'm going to try, shall we say, this is sort of putting the known things to the test. What I've got in the printer at the moment is, it's still PLA, but I'm basically doing everything that you would do to try and make a part as strong as possible. So we are talking 5-layer wall thickness, we are talking 60% infill, we are talking absolutely massive infill overlap into the walls, and I'm talking like 40% overlap, which is heaps. And also a really fine layer height. So these I've only done at like 0.2, just because, all right, so 0.4 tip, but 0.2 layer height. This one that's in here at the moment is running 0.1, half, yeah, 0.1 layer height. So it's going to come out looking pretty silky smooth. It should look pretty silky anyway, because it's silky PLA. So we'll try that. Now, the problem I've got is I would love to go in the kitchen and do this in my oven, but my oven is actually a piece of junk and it's not really good at holding a good temperature. So I'm actually going to go outside today and do this in the barbecue. I think I can keep a more constant temperature in the barbecue out the back. I'll take my thermocouple out as well, just to keep an eye on things. But yeah, I reckon I've got a better odds of doing it out there than I do in the kitchen with my heap of crap oven. Plus, you know, you put pieces of plastic in the oven in the kitchen and certain things happen when your wife walks in the house, and you know what happens. Anyway, so I suppose the best thing to do is fire up the barbie out the back and we'll go outside and we'll have ourselves a PLA barbecue. How's that sound? Okay, so we got part number 1, just standard annealing. So the go is with this, put it in oven or whatever, 190 degrees. As soon as it goes in, turn the heat off and just let it sit for half hour until the oven goes cold. So that's what we're going to do. We're just coming down to about the right temperature, so we're going to get that ready and bung it in, let it go and see what happens. Okay, so that's come back out. Honestly, it doesn't look any different. I was kind of hoping it would have smoothed, or I was kind of hoping something would have happened. It looks like that bottom, the 2 bottom bits there have peeled up a little bit. Honestly thought it was just going to melt. Let's see if it's... Oh yeah, no, we've got a little bit of meltage on the bottom and a bit of the infill sag showing, and there's 4 layers on the bottom of that. So oh well, we'll get the other one in and see how it goes. Right, so apparently the go is to get a container of sorts, get some flour in there, pack it down as best you can before you put the part in. So sort of just tamp it down with a bit of wood, just, you know, almost like you would see people doing that, cast their own steel, cast their own cast iron parts and stuff. And then we get the part in there and then fill it all in with flour, just compact on top of that, and then we stick it in the barbie again for 190 to 200, and leave it at heat for half hour, then let it cool down for half hour. So here's hoping. Rightio, she's out, done. It's definitely cooked. We got some brown flour. Let's have a dig around in here, and I was going to go straight in with my fingers, but I was actually surprised. The pan's cooled down quickly, but I'm surprised at how much heat the flour itself has retained. And the flour's kind of like, it was very difficult to compact it before, and it's kind of almost like cooked itself together. I'm going to need more tools. Give me 2 secs. Rightio, we're back with a sharp thing and a tripod. Let's have a crack at this. Oh, 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 it's still soft. Maybe I should let it cool down a bit more. Nah, you know what? That's still bendy. That's still partly plasticized. I'm going to dig some of that flour away without disturbing the part, and I'm just going to let that cool right down till it's cold. There is no way it's not solid yet. All right, we'll be back. Okay, this has cooled down a lot more. We have a bit more of a poke at it. The rest of this flour is actually, it's like kilned it. It's gone rock hard. So we'll get the rest of that off. I'll give it a bit of a clean or whatever, bit of an old wash, or just to get the rest of the flour off. See, some of the flour's actually melted to that by the look of it. It's not just stuck to it. It's like, oh no, here it comes. So yeah, we'll get that cleaned up, and then we can get all 3 of them side by side inside and have a look see. But yeah, look at that, that's all. Didn't know flour did that. Who knew? Okay, trendsetters, we are back inside, having completed our annealing processes outside in the trusty barbecue. So they're done. Also, my other one that I did, as previously mentioned, is finished. So this is the other one that I did. So this, again, it's just PLA. All right, fair enough. It's not the same stuff as them, but this I'm going to treat as a, should we call it, another control. So I'm not going to do any annealing on this one. But this one, I've just gone absolutely burko with the strength of it in terms of how you would set it up to print in your slicer. So we're going to test that one also, just to see, I suppose, more how this one stands up against that one, or I don't know, all of them, whatever. We'll head on over to the vise. I don't have any real scientific equipment to test all of this stuff. I got a cheap $2 crappy hanging scale, so we'll try that. Apparently it's supposed to be in kilos, but I'll take that with a very big pinch of salt. So yeah, we'll head on over to the vise and we'll break some stuff. How's that sound? All right, we've got all this stuff set up here. We've got our control part in the vise ready to go. Just let me be clear, nothing here is scientific. I have a garbage scale and I'm using little scraps of pipe to break this stuff and what have you. The length of this and that distance there is roughly 10 centimeters, 100 mil, and we're measuring in allegedly kilograms. So this is going to come out dangerously close to, shall we say, Newton meters of torque to snap these bits and pieces off. So, but as I said, big pinch of salt. So let's just see how we go. I'm not going to film testing all of them because that would just take forever. So we're going to do the control, and then I will go ahead and do the other ones off camera, and we will tabulate the results over here. So let's start winding. So I just got a little turnbuckle just out of frame here, just to gradually apply pressure to this. Even that's already starting to. We're at 1. Whoop, there it goes. So bit over, we'll say bit over 1, being generous. Yep, that's failed. Let's go. You know what I didn't think about is how the hell I'm going to get. Oh no, that'll come out. No, that's going to be a Monday to get out. Control. What do we say? We'll say 1.1-ish. Sort of. Okay, now the whole idea behind the oval shaped one was because we got a similar cross section that way, but obviously it's wider this way. So the round parts are 8mm round. These are about 14mm. Oh, this is going to be, you didn't think this through, did you? Way to go, Bill. Oh, unwind it. Half a kilo. 1 kilo. 1.5. I'm trying my best not to help this in any way, shape or form. I'm just holding the scale so you guys can see what's going on. 2. Things are clunking. Hope the scale doesn't break. That would make life bad. That part's really starting to deform in the, I don't know if you can see it just under my arm, it's actually squeezing itself because of the force on the, it's pretty strong. But that was kind of part of the test as well. 3.5, man. Oop. Okay. 3.5. All right, so round, oval. That was pretty impressive. Now the next thing we've got is, I'm going to say, you can't really see that, can you? We've got here our round, our oval. We've got a sharp corner on each part, and then we've got a fillet. There we go. All right, and then the top. Now the top's going to be a little interesting because the plan is, get that out of the road. So I've printed a special little tool to snap these off, but if you've been playing along at home, you'll notice that one of these has got a nice little sharp edge in it, a little sharp corner. The other one has a fillet. All right, so we'll see how those go. That edge, that sharp edge there, was more to see with the other parts what happened to a sharp edge in the heat in the oven. But you can see that top bit has already bent where that bit's been reefing on it. So we'll flip it around. This might get interesting. You know what? I've kind of stuffed myself up here because my little tool that I made only just fits in there without that having been bent. I'm going to have to open that up. Will that skew the results? Who knows? Alright, here's my little special Deschel thing tester. So again, this part here is 10 centimeters long, from basically from that surface there to where the scale will hang onto it. Let's unwind again. Why couldn't I have made something motorized that does this like quickly? Why did I have to go down the road of a M5 turnbuckle? What was I thinking? Oh, bit of preload there. Alright, so we're already at half a kilo. Straight off the hop. One. Whoop. What was that? About 1.25. I'm going to leave that for a minute. I'll go back through the footage afterwards and check that. I've got to be honest, I wasn't paying attention. Not for that, anyway. Other side. I knew what I was doing. Again. Just forever unwinding threads for a stupid $2 scale. Okay, bit of preload, never mind. One. 1.5. 1 3/4. I can hear crunching. 2. I was expecting the filleted edge to do better for obvious reasons. Pardon my stomach. 2.5. Okay. Whoa. I think something's given up because scale just died down a bit. And it's not my tool. Not my little snapping tool. Yeah, no, that's failing. That's just slowly starting to fray. There she goes. So I'm going to say 3, conservatively. As I said, we're not getting too carried away with this. So 3 for that. I'll come back to that one. Now this one, this middle part, I did have plans to, sort of, the idea was to try and twist it off to see whether the thinnest part of the print would break, or whether a layer either side would let go. I might leave that for now. I think we've, yeah, that's given it up. So, mind you, that took a little bit of extra effort just to finish off the job. So, all right, well, that's the control done. That gives us some numbers to work with. I'll do the rest of this off camera, and then we'll come back and we will do some mathsing and look at the results. Okay, kids, I promised you scattered results, and that is exactly what we've got. Lord knows the equipment I was using was not exactly up to scratch. And if we're talking ballpark figures, we're talking about a ballpark with very, very low fences. These results are all over the place. I took all the measurements, Newton meters, whatever you want to call them. Rather than sort of trying to put it into a graph or anything, I basically just worked on a ranking system. So basically 1 being at the highest measurement, 4 being the lowest measurement. So basically strongest through to weakest. All right, let's just whiz in on this a bit here. So across the board, we see, the control. You would think if you're annealing a part, if it's going to get stronger, you would expect that to have a fairly low score, yet it was second highest. All right, and the highest, oddly enough, was the silk one. I'm not really paying a lot of attention to those silk results, because being that it's a different filament, and this stuff it's a lot more brittle than the grey stuff. The grey, this is actual like Creality brand prototyping filament. It feels just a bit softer and a bit more, a bit not quite as brittle as this stuff. This stuff is like, it's terrible. But yeah, so let's just cover that up for a minute. If we have a look across the board here, everything is just all over the place. We're seeing reasonably good results for when we're getting into these sorts of areas with, with the annealed with flour. All right, so that's noteworthy. Then sort of quite adversely, these bits that we were breaking off the top, the control seemed to do a lot better, and your standard sort of, I don't know, everything was a bit all over the place. It almost seemed as if with these top pieces, the two annealed pieces, they were a lot more brittle and they just went bang and snapped off. Yeah, so I might have to revisit this. These results are, yeah. I mean, I love good data and I like consistent data, but I don't think this is consistent data. So we might have to revisit this one. Well, trendsetters, I think today's video has basically wound up probably creating more questions than answering any. But that's not a bad thing. Sometimes that's good. We will come back to this one day, I think, and yeah, maybe with some slightly more Skookum equipment, and just, you know, have another go at it and sort of see if we can get some more scientific data, you know, and just make sure everything's, you know, up to scratch, as it were, and not like whatever that was that I did before. Yeah, I guess the best thing to say is thank you very much for watching. I'll see you in the next one.